Say that again, please. I'm ready. I can start? I don't think I can start yet. I'm waiting for my cue. Okay. Thank you very much. I'd like to thank the organizers for inviting me and bringing me here. I would like to thank the musicians who worked so hard to play my music last night. And I'd also like to thank the several people in the audience who have inspired me or helped me. This includes Rick and Cliff Callender, a longtime collaborator, and Noam Elkies, who's helped me work through some of the math that I'm going to talk about today. The title of my talk is Vectors and Voice Leading. If we think about informal musical talk, there's a lot of terms that intuitively refer to musical objects, which we can think of as points in a space. And these include terms like note, chord, chord type. And these all refer to some sort of singular musical object. We also have musical terms like interval, chord progression, and voice leading. And these intuitively seem to refer to transitions from one object to another object, or what we might think of as vectors. Sometimes it's pretty obvious how to construe a musical vector. So if we have a note like middle C and the E above it, the vector between them, we think of it as the interval of an ascending major third, and there's no real problem formalizing any of this where it's really one-dimensional real affine space, and it all makes sense the way we would expect. In other cases, the interpretation of our ordinary talk about musical vectors is a little harder to figure out. We talk a lot about voice leading, and we would like to think of voice leading as some kind of route from one chord to another, but it's not really at all clear how to spell out this intuition. So this is a problem that music theorists had been working on for several decades, trying to come up with a reasonable formal theory of musical vectors. I would say that the initial efforts had only limited successes for a couple of reasons. One is that theorists didn't try too hard to explain which particular sorts of musical vectors were fundamental to musical thinking, to composition, or to analysis. And one reason for this is kind of interesting and goes to explain or to illustrate how issues like mathematical taste can have a big impact on the history of a field. One very influential music theorist, my teacher David Lewin, had a mathematical taste for abstraction. And when he was trying to formalize the idea of vectors, he wanted to remain deeply neutral about what musical vectors might be. And you can make an analogy here to something like category theory, which talks about objects and arrows, but essentially imposes a very minimal sort of structure on what the arrows might actually be. Interestingly enough, Lewin promulgated formal tools that inadvertently prevented people from adequately formalizing a central class of musical vectors. And I want to give an example of that now because it'll help explain where I'm coming from. One of the most basic music theoretical acts that we engage in is to ignore octaves. So instead of talking about this C or that C in that octave, we want to talk just about C in general. And this means instead of thinking about the space of music as a kind of line, the line that's represented by the piano keyboard, we like to think about the space of music as a circular structure where each point represents a note when you are ignoring octaves. Interestingly, traditional music theorists, at least in America, recognized only one way in which you could move from one point on the circle to another, only one way to move from one pitch class to another. So you could illustrate this by a kind of movie. Here we are occupying the point representing C on the pitch class circle, and then something happens, and we show up at E. How did we get from C to E? Did we move clockwise by 4 ascending semitones? Did we move counterclockwise by 8? According to traditional pitch class theory, that is not a sensible question. There just is no, it's not well formed. You should not ask or try to answer that. You are at C, you move to E, and that's all there is to say. Now, this is really kind of strange because in informal musical talk, we really do talk about, say, being at G and moving down 4 semitones to E flat. You might say that a central pitch motif in Beethoven's Fifth Symphony is that motion, and it happens in many different octaves, but it is importantly different from. So this is not really a very strange thing to want to talk about. And what's actually quite interesting is why it is that music theorists felt they could get away without talking about that. And I have some conjectures about this, which I will just remark on. One really interesting thing is that the founders of modern American music theory were all 12-tone composers. And 12-tone music is almost unique among all the musical styles in the world and in history in the extent to which it ignores octave relationships. So in 12-tone music, being at C in any octave and being at D in any octave, moving from C in any octave to D in any octave, is a syntactical thing. And we really are, when listening to 12-tone music, supposed to imagine all of the following transitions as fundamentally the same. This is a very, very, very interesting and very, very particular feature of 12-tone music. My conjecture is that many of the founders of American music theory had absorbed this feature so deeply that it became something that it was a little bit like the water that a fish swims in, that maybe they didn't even think about how unusual it is and how different that musical grammar is from musical grammars like Beethoven's, where it makes a difference how we move from G to E flat. Another interesting fact is that many of the founders of American music theory were, just for historical reasons, they were most comfortable with and had a taste for discrete mathematics and in particular group theory. They may not have had a lot of exposure to geometry. For whatever reason, they felt most comfortable representing the pitch class circle as a mathematical group rather than, say, as a manifold. So at a certain point in my life, maybe 10 years ago or a little bit more, I felt unsatisfied with this situation, and I decided that I had to go back to the drawing board and think again about one of the most basic music theoretical objects, namely the pitch class interval. And I decided we had to get rid of this idea of there being only one way of moving from G to E flat and replace it with something a little more flexible. So I concocted the idea of a path in pitch class space, which shows how one point on the circle moves to another, and it corresponds to simple musical ideas like whatever octave this G is in, it moves up by 8 semitones to E flat, and that's one path in pitch class space. Or G, whatever octave it's in, moves down by 4 semitones to E flat, and that's a different path in pitch class space. Now, of course, those of you who know mathematics realize that this concept is essentially the concept of a vector in the tangent space of the circle. It's a really basic concept in geometry. And in musical applications, we can draw a connection between these vectors in the tangent space of the circle and certain kinds of unidirectional paths on the circle. So we can visualize these paths in pitch class space in a couple of different ways. Up at the top there, I imagine that we have an actual line, a flat space, attached to the pitch class circle at G, and this flat space, this line, contains vectors like +8, -4. Alternatively, you can imagine actually moving on the pitch class circle, almost as if you're glissandoing, and we can distinguish all the different ways in which G can move to E flat. Down by 4 semitones, -4, up by 8 semitones, +8, or the various ways in which you can wrap around the circle. So you could go down by 16 or up by 20. And this allows us to say, well, in Beethoven's Fifth Symphony, one of those particular paths is particularly important, namely the -4 path. So this is a perfectly sort of straightforward notion. I imagine all of you think it's totally simple. It is interesting that when I first started talking about these, I met a lot of resistance from older music theorists who had grown up with the older conception of pitch class intervals and would try to argue with me and say that this was really nonsensical. It made no sense. It was just a meaningless set of distinctions. And I don't think it is meaningless. And in fact, it corresponds to really, elementary concepts in geometry. Okay, once we have these paths in pitch class space, we are in business because we can use them to formalize what we're talking about when we're talking about voice leading. For me, a voice leading just is a collection of these paths in pitch class space. Formally, it's a multiset. And it shows how the notes of one chord move to the notes of another. And these things are really, really quite elementary. Here's an example of a voice leading. C major, the triad, C, E, G, moves to F major, the triad, by keeping the root fixed, moving the third up by semitone, and moving the fifth up by 2 semitones. You can think of it as a schema for getting from one chord to another, which composers internalize. And so this voice leading can be expressed in many different ways, like so, or like so, or like so, but not like so. Okay, so all of those, the first 3 things I played were examples of this voice leading. The last one was not, because there the notes move along different paths. And we can write these things down. To express this voice leading, I write C, E, G goes to C, F, A, and I put the paths up top. This says C goes to C by a path of 0. This says E goes to F by a path of 1. This says G goes to A by a path of 2. And since this is kind of a fussy and cluttered notation, in the case where notes move by the shortest possible path, which is typically the most common one, I leave out those numbers. So if the numbers aren't there, the shortest path is assumed. So now what we are doing is attaching 3 real numbers, a collection of 3 real numbers, to some sort of 3-dimensional space representing 3 note chords. And again, we are talking about vectors in the tangent space of a manifold or of a geometrical object, which, as Rick mentioned, is actually an orbifold because it will contain singularities. So that is the notion of voice leading. I think it corresponds pretty well to the kind of talk you find in theory textbooks or composition lessons where people talk all the time about voice leading and mean to be talking about specific paths from one chord to another. Okay? So this is not, in my view, an esoteric theoretical concept. So suppose you have a theory of voice leading. What can you do? Well, wonderful things like count them. You can count voice leadings. You can come up with theories about voice leadings. And, maybe most sort of spectacularly, you can use them to define a genuine geometry of chords and chord types. Now, I'm going to talk about counting voice leadings because this is a subject that is really exciting me. How do you count voice leadings? What are you talking about? Well, to count voice leadings, you need 3 things. First, you need a gigantic number of musical scores that are in some sort of computer-readable format, like music XML. Second, you need to analyze this music by hand, identifying each of the chords and all of the keys, so that the computer can tell exactly where you are, what chord, what key at every point. Third, you need to spend a lot of time programming your computer. And so this is what I've been doing over the last maybe 5 years, assembling a database of pieces from Dufay all the way to Brahms, about 1,000 pieces, analyzed by hand and also analyzed by some people who've helped me, including some people in this room. Here's the snapshot of the corpus as it currently exists. Blue, so we have the composers down here, and I show how many chords of music I've analyzed by these composers. Blue is major mode, including Mixolydian. Green is minor mode, including Dorian, Phrygian, and so on. You can see I've done the most with Bach. I've analyzed all 371 chorales in the Riemann-Schneider edition, all the Mozart sonatas, a third of the Beethoven sonatas, a whole bunch of Monteverdi, Palestrina, Dufay, Josquin. So we have a pretty big database of music, where you can start to do statistics and learn about how composers move through musical space. And this allows us to answer questions that I find to be interesting. Let me give you a few examples. You might ask, in Bach's music, does the tritone have an intrinsic obligation to resolve? We know that in a 5/7 chord, the leading tone and scale degree 4 tend to resolve inward. And you might wonder, is there something about that tritone that is fundamental to Western tonality? And the most popular and most accurate English language textbook is quite unambiguous on this point. It says, yes, tritones resolve, and that has to do with the tritone itself and not the nature of the 5/7 chord more specifically. So according to our best textbook, this voice leading over here is the normal one, because here we see a resolving tritone. And this voice leading over here is not normal, because here the tritone is treated irregularly. Instead of resolving downward, it actually moves upward. So we can do the statistics, we can count all of the occurrences of this chord progression in Bach, and we can ask, does Bach tend to resolve the tritone? And the answer is no. In Bach's music, this voice leading is, in fact, more common than any of the ones in which the tritone resolves. Now, you might think that this is just a pedantic point about a certain sort of chord progression in Bach. If you think that, I'm not really going to argue with you too much, but I actually think it goes to a very deep point about where functionality comes from and about whether this tritone interval has an inherent tendency to move. Many theorists have thought that the tendency of this tritone is definitional of tonality, and you actually can see in Bach's music that that seems not to be the case. So I'm a nerd. I get interested in questions like that, detailed questions about how the music works and what the underlying principles are. Let me give you another example of a question. You might ask, is the standard 4/1 progression quintessentially neighboring? Okay, so does the 4 chord inherently require or lead you to expect a certain kind of voice leading where scale degree 4 goes down to scale degree 3, scale degree 6 goes down to scale degree 5, as on the left here? Is that the essence of the 4 chord? And again, many theorists have said yes. Schenkerians think that the 4 chord really is fundamentally a neighboring progression. It's not a truly harmonic progression. It's a kind of neighboring activity that happens to produce the appearance of a chord, but it's not a true chord. Dan Harrison, Rick's colleague, and a mentor of mine, he has a whole theory of subdominantness that involves these particular voice leading motions. So you might ask, again, now that we can formalize and count voice leadings, you can say, well, let's just look. How do different composers treat the 4 chord? And the answer here is actually even more interesting than the previous answer, because it turns out you can't give a single answer. It turns out that for composers of the Renaissance up to and including Bach, you find a wide range of treatments of the 4/1 progression. So usually Bach does that thing on the left, but there is also an alternative and ascending resolution of the 4 chord that is quite common in the music of Palestrina, of Thomas Morley, of Monteverdi, and quite common in the Bach chorales, and that's this thing on the right. And this is quite an interesting chord progression because it actually introduces a leading tone and that tritone that people take to be definitive of dominantness. So it sounds a little paradoxical, but it's entirely accurate to say that in the Renaissance and even in early Baroque tonality, the 4/1 progression is not strongly differentiated from the dominant tonic progression, and 4/1 progressions often have more than a whiff of dominantness. Now, what's kind of amazing, and what I did not expect, is that this view, this treatment of the dominant chord, essentially is exterminated between Bach and Mozart. Mozart almost never does this. Mozart, Haydn, Beethoven. For them, the 4-chord really is this and not this. So that's an example of how statistics and being able to count voice leading can lead you to understand this sort of subtle evolution that continues through the tonal era and indicates maybe a really different way of conceptualizing some of these basic musical progressions. Okay, so that's counting voice leadings. I, being a nerd, love to do stuff like that. I now want to give you my second illustration about what you can do if you can really talk specifically about voice leading, and just talk about the kinds of things, just ways in which you might start to classify and theorize about voice leading. Here we have a voice leading between an A major chord and an E major chord. It often appears with passing tones here. So A and C sharp move down, and then there's another C sharp and another C sharp and E, and they move up. Okay? So this is what I call a canonic voice leading. Now that sounds a little funny because a canon is something that is extended in time, as we heard yesterday, whereas a voice leading is a much more localized, instantaneous thing. What do I mean by a canonic voice leading? Well, a canonic voice leading is a voice leading that has two properties. One, it connects two chords that are related by transposition. Here we have a major triad with a doubled third, and it moves up to another major triad with another doubled third, that's important, by 7 semitones. So this thing can be iterated. It leaves you where you started, meaning you can do it again and again and again. The other thing about this canonic voice leading is it cyclically permutes the chordal elements. So if we label root, third, second, third, fifth, 1, 2, 3, 4, we see it sends root to third, it sends third to fifth, it sends fifth to the second third, and it sends the second third back to the root. So that is the permutation 1 going to 2 to 4 to 3 to 1. What this means is that if you iterate this voice leading, each of the voices will move through each of the elements, each of the components of the chord, and that means you will create a canon by iterating it. Does everyone see why that is the case? Does everyone think that if they go home and think about it for a little bit, they will see why it is the case? It is the case. And what's even more is Bach knew it was the case. So if you use the standard passing tones and you iterate it, each melody plays this, essentially. And there are a number of places in Bach's music where he uses this voice leading repeatedly, creating a canon that is to various degrees disguised. I'll play for you what the canon sounds like. Okay, that's the pure canon. At the end of Bach's chorale number 15, he slips this canon in without making any fuss about it. You would never, ever notice it unless you are a true crazy person like me and stares at Bach chorales over and over again for hours. And here's a place where that voice leading gets repeated 4 or 5 times, disguised because he has to work with a melody he did not compose, but definitely there once you start to look for it. Okay? It's this wonderful moment because it's a moment of incredible contrapuntal artistry, unbelievable technique and beauty, and it's tucked away in a passage where no one, maybe except me, has ever noticed it. And it's as if you're in one of those frescoed Renaissance palaces, and tucked away over in the corner, you just notice the most beautiful painting that you've ever seen, but it's behind a potted plant and no one would ever see it. It's an excess of musical genius of the sort that really makes me get goosebumps. All right, these canonic voice leadings are all over the place. Sometimes they happen from the first chord to the repetition of a chord in a repeating progression. So here is a very common pop music progression that, given how it is instantiated by the music, it is quite easy to hear a canon sort of tucked in there. So it's a 1-5-4-1 progression. And as the progression repeats, you hear a voice leading from D to D that is one of these canonic voice leadings. And there's a very funny way in which this G gets tucked in above the main vocal line, and so you almost don't notice it. So I'll just play, this progression occurs all over the place. This is Neil Young, Helpless, and I will just, hopefully you can hear the canon. D, D, D. So this canon is an unintended but not accidental feature of the kinds of things that Neil Young was thinking about in this music. In the piece you heard last night, it starts with exactly this canon, and the canon goes through these various rock progressions. You can find these canons all over the place. There's one in 8 Days a Week. There's one in all sorts of pop music songs, and they just sort of come naturally out of certain kinds of repeating progressions. Once your ear and brain is sensitized to them, and once you overcome your sense of disbelief, which I remember having, you start to find these things and realize that they're a natural byproduct of certain kinds of musical exploration. Okay, so I could talk more about this, but I'm not going to. I want to just leave you with the final thing that you can do once you have a good notion of a musical vector, is you can use it to make the transition that Rick was talking about from a kind of abstract, graph-theoretical conception of musical structure to something that is genuinely geometrical in the most robust sense. So I essentially, and this is a work that I did many years ago with a lot of help from Gnome and a lot of collaboration with Cliff, Ian Quinn, and I published an article in Science Magazine sort of talking about the general connection between musical terms and geometrical terms. The most important correspondence is between chord and point in an orbifold, voice leading and vector or certain kinds of paths in this orbifold, and scale, like C major scale, and metric. And the wonderful thing about this correspondence is it's essentially idiomatic on both sides, by which I mean these terms over here on the left really are standard idiomatic music theoretical terms, the sort of thing you really teach to kids when you're explaining music theory the first time. And you don't have to stretch them or bend them or make them into something they're not in order to make this correspondence work. And then meanwhile, on the mathematics side, these things are not, these things are pretty standard undergraduate math objects, and you don't have to do a lot of fancy footwork to associate these two things. There's a natural translation between what musicians are doing and what geometers are talking about. And really central to this whole way of thinking about music is what I call the golden rule. To get a really good geometry of music, you want to create spaces where every point represents a chord, or chord type, depending on what kind of space you're dealing with, and every line segment represents a voice leading. So the wonderful thing about these spaces is you don't just have points, but you actually have vectors and paths doing exactly the work we intuitively want them to be doing, representing the transitions, specifically musically useful kinds of transitions from one chord to another. And the really hard thing in making this all work out was to get the concept of voice leading, to formalize correctly the concept of voice leading, and to associate it with vectors and paths. And this could really only be done if we went back to the drawing board, got rid of the traditional music theoretical pitch class interval, and replaced it with something else. So here is the Mobius strip that represents two-note chords. Here is the resolving tritone that I was talking about a moment ago. This is a vector in the space, and we have all sorts of familiar geometrical phenomena. For instance, when you transport this vector to another point, the result you get is dependent on the path. If you transpose upward, the tritone at C F sharp resolves to D flat F, but if you transpose downward, which corresponds to sliding it off the left edge of the Mobius strip, that same tritone now resolves to G B. I'm not going to take a lot of time with this, but if you go to my website, you can download a little computer program. It allows you to explore the geometry of these musical spaces. This is 2-note chord space. It is a Mobius strip. You can see that you can put voice leadings in on the keyboard like this, and you can see exactly what path each voice leading corresponds to. You can do that for, this is 2-note chord space. That's 2-note set class space, where points represent not particular intervals, but interval classes like major third, minor third. Here is the 3-dimensional 3-note chord space, naturally containing within it the cube dance graph that Rick Cohn was talking about. You can zoom in, you can show whatever chords you want. You can look at a space of 3-note chord types where a point is a major, all major triads are collapsed to a point. It looks like that. And you can look at 3-note set class space. This is a space Cliff Callender first discovered, or you can look at a projection of 4-dimensional 4-note chord space. So I'm not going to show that to you any more than just tell you about it. Uh-oh. Come on, computer. What does the geometry allow us to do? Well, one cool thing is we can build sculptures and other artworks. So here is the space of 3-note chord types. Every ball there represents a kind of 3-note chord type, like major chord, minor chord. You can actually go to the National Museum of Mathematics in Manhattan, which is not as close as it usually is when I give this talk, I admit, and you can go see this thing, and in the sculpture, each of these balls is a theremin. So that means you can go and touch the major triad and hear it. There's a little laptop hidden in the podium, and it makes the sound of the major triad. And so you can literally have this hands-on musical exploratory relation to the geometry of 3-note chord types. This is really just the tip of the iceberg. There's a whole world of musical / geometrical exploration that could be done using these kinds of ideas. Another thing you can do with the geometry is answer basic theoretical questions about the nature of music. For instance, how is it, under what circumstances can we link similar sounding harmonies by small voice leadings? You can understand the logic that underlies specific pieces. So I've got animations that talk about the logic of the Chopin E minor prelude or Debussy's L'Île Joyeuse or a ton of other pieces. We can understand the origin of many seemingly independent graphical depictions of musical structure, cube dance being one. So basically, 15 years ago, we had a profusion of different kinds of music theoretical graphs that all depicted little parts of musical structure, and now we're in a position to realize that those are all just sort of different ways of looking at the same small family of geometrical spaces. So there's a lot of stuff we can do with this, but you know, I actually think that all of these are the wrong answer. The right answer is that understanding the connection between music and geometry, understanding the translation manual that allows you to see that these idiomatic terms in the one domain correspond to the idiomatic terms in the other domain, is intrinsically beautiful. That's what intellectual life is about, is understanding things at a very deep level and realizing that they are beautiful. That's why we listen to music, because these abstract patterns move us. And when we hear a Bach fugue or even a silly little chorale, we are sometimes moved by the incredible beauty of these patterns. And that's why we do mathematics too, right? Because we find these deep explanations and correspondences and relationships and theorems, we find them to be beautiful. So I actually don't think I should be in the position of arguing with you that this will help you analyze this piece or that piece. I say, if you don't find this beauty, you're missing out on something profound, and so I encourage you to do it again. Ultimately, what we can start to move toward is a deeper appreciation of how composers' choices are constrained by the logico-geometrical structure of musical possibility. So instead of seeing composers as acting in a frictionless plane in outer space where there's no resistance and all motions are equivalent, we can start to come to see them as moving as rock climbers on a rock face, where the rock face has a kind of intrinsic structure, and there are handholds over here, and there are smooth spaces over there, and the rock climber's free action is necessarily influenced by the pre-existing structure that he or she is engaging with. And so in this metaphor, the logic of musical space offers composers certain kinds of handholds and blocks easy traversal of certain kinds of other routes. And once we understand this logic, we get, in my experience, a very different kind of relationship to the analysis of music, because we start to appreciate why certain choices were made the way they were and had to be made the way they were. So, what can you do with a robust formal theory of voice leading? You can count them, and we saw that this helps us understand where the tritone comes, what the tritone is all about, helps us understand the humble 4/1 progression. We can theorize about them. I gave you a little glimpse with this idea of canonic voice leadings, and last night you heard how a 21st century composer can use the idea of canonic voice leadings to create music that hopefully sounds like 21st century music. And then we can use these ideas to define a true geometry of chords and chord types. If you are interested in this geometry, I've written a whole book about it that is pitched at the undergraduate level. I do my best to answer questions from confused readers all over the world. I get emails from, a teenager in Iran who says, "What do you mean on page 47?" And I do my best to answer that. So I make this promise to you: if you put in the effort to try to understand the geometry of music, I will put in the effort to answer emails at least up through your first 3 emails. Okay, thank you very much.
The next speaker we have is Jean-Louis Giavito from